third video for this unit is going to build on video number 2, where we learned how ions are formed from neutral atoms. And now we're going to look at how ions like to interact with each other to form what are called binary ionic compounds. So let's begin by first of all defining what is this word binary. Binary simply means two. So these are compounds that contain two different types of atoms. But more specifically, the word ionic means that they must be charged species. And so in order for them to bond with each other, one must be positive and one must be negative, and therefore they're held together by the notion that opposites attract, or in chemistry terms, by electrostatic forces. So what I'm going to do is I'm going to begin again with Bohr-Rutherford, but we will convert into Lewis structures to make life a little easier as well, just to show you what's going on here of how cations and anions can come together to create ionic compounds. We're going to begin with a lithium and fluorine combination. So for lithium, we know that there are 3 protons and 4 neutrons in its nucleus from using the periodic table. And we know also that there are 3 valence electrons. 1, 2, 3. We also know, sorry, not 3 valence electrons, 3 electrons in total. One of those is a valence electron. And we also know this connection that there's one of them because it's in group 1 of the periodic table. And all elements in that particular column, when they form ions, all have one electron in the outer shell that can leave. And we'll get into that in just a moment. On the other side over here, we're going to choose fluorine as our nonmetal. And fluorine is element number 9, and it therefore has 9 electrons altogether. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 7 of those are in its outer shell. And of course, the really cool connection here is that when you look at where it is on the periodic table, it's also in column number 7. So the column number that it's in corresponds to how many electrons are in its outer shell. Now, both of these atoms want to become ions or want to have a full outer shell, and they do it through different ways. We know that the metals on the periodic table like to lose electrons, whereas the non-metals like to gain. And so how can these processes complement each other? Well, if we take a look at lithium, we can see that its outer electron would like to leave. And that, therefore, is going to leave us with lithium having one more positive than it does negatives. But this electron doesn't just hang out in outer space wherever. It comes near fluorine, which is more than happy to accept it because once it does, it will have a full outer shell. And therefore, we have what is called the fluoride ion, or F1-. And so these two complementary processes are great. One likes to lose, one likes to gain. And so these two can come together in a one-to-one relationship of Li1 plus F1-. Although in the chemistry world, we don't need to show those charges to communicate that they come together in a one-to-one ratio. Once we've established what those ratios are, we can simplify this simply into a chemical formula of LiF. And when there are no numbers down here in subscript form, we assume that they are ones. And so lithium and fluoride come together in a one-to-one ratio. Now, to name this compound, we're going to use the other side of your alchem table, the table of ions side. And if you look at Li1+, you will discover that its name is lithium. Now, this can be a little troublesome sometimes because the name of a lithium atom is the same name as we give to its respective cation, Li1+. Nonetheless, the word lithium can have both meanings depending on what context you're using it in. If you go on that side of the periodic table, though, and you look at the fluorine ion of F1-, you'll notice that there's a slight change to its name, as there is with all of the other nonmetals when they become anions as well. You'll notice that their element names change. Instead of using their usual endings, you'll notice that their endings are dropped, and the suffix IDE is put in place. So we know in this case we're not dealing with just fluorine by itself. It's bonded through electrostatic charges with lithium, and we're going to call it fluoride. Because again, we're dealing with F1-, not just F. And this is how we come up with chemical formulas right here and their corresponding ionic names here. let's look at another example. Here we go. Let's look at beryllium and oxygen. So beryllium is element number 4. So it will have 4 protons. It will also have 4 electrons. 1, 2, 3, 4. And when we round its atomic mass number, it becomes a 9. And so 9 minus 4 means that there would be 5 neutrons in this particular atom to start. Now, again, when we focus in on that outer shell, we notice that there are 2 electrons in it out of a possible full shell of 8. So we could either gain 6 or lose 2. Beryllium says, I think it would be much easier if I were to lose 2. So we're going to take those 2 valence electrons out of there for just a moment, and we can show, using Lewis notation down here, that what remains is beryllium with a charge of 2+, because there are 2 more positives than negatives overall. Now, oxygen is element number 8, and it has 8 protons, and its mass number, which is 16, minus 8, tells us there would be 8 neutrons. And to counterbalance those 8 protons, we would also have 8 electrons. So 1, 2, 3, 4, 5, 6, 7, and 8. So again, if we draw our attention to that outer shell and ask ourselves, how can we make it full? We have 2 options. We could either peel off all 6 of those electrons that are in the outer shell to show that outer shell that's full underneath it, or we could add 2 to get 8. Well, lo and behold, there are these 2 electrons out here that were donated from beryllium, and so let's take them and put them into these spots here to create a full outer shell. And so we can illustrate this using Lewis notation by using the symbol O2-, because there are now 2 more negatives than there are positives on those structures. And lo and behold, for both of these to achieve full outer shells, it took a 1-to-1 ratio of beryllium atoms to oxygen atoms to create the beryllium ion or beryllium cation and the oxide ion. And so we don't need to show these charges per se overall. We can simplify this to simply BeO, a 1-to-1 ratio, 2 electrons lost, 2 electrons gained. And we can name it using the ion side of a periodic table. So you'll see that the name for this portion right here is called, surprisingly not, beryllium. And the name for this portion here, because it's a non-metal that gained electrons, is no longer oxygen, it's oxide. So the name of this compound is beryllium oxide. All right, I'd like you to try a few more examples to see if you have the right idea. I'd like you to try aluminum with nitrogen. I'd like you to try potassium with sulfur and magnesium with phosphorus. I'm going to model the first one with you, but instead of using Bohr-Rutherford this time, let's use Lewis dot diagrams. And then I'd like you to pause the video after example A, try B and C, and then click it on again to see if you did it right. So let's begin with aluminum and nitrogen. If we look on the periodic table, aluminum's symbol is Al, and because it's in column number 3, we know that there are 3 valence electrons in its outer shell. Look already how much easier this is than drawing Bohr-Rutherford diagrams. So no more Bohr-Rutherford after this video. Now, nitrogen is a nonmetal. It's on the other side of the staircase. It's in group 5, and so that would mean that it has 5 valence electrons in its outer shell. And so let's ask ourselves, how can aluminum and nitrogen complement each other so that they both get full outer shells, but there's no AWOL electrons? Every electron that's lost by the metal is gained by the nonmetal. Well, sure enough, we notice that aluminum could lose an electron, and it could go to nitrogen right there to help contribute towards its outer shell. And similarly, this one could leave and go here, and this one could leave and go here. So what does this mean? It means we now have aluminum with a charge of 3 plus because it's lost 3 electrons and now has 3 more positive charges than it does negatives. And we end up with nitrogen having an excess of 3 electrons, which is all right. 3 electrons lost, 3 electrons gains mean, hey, all electrons are counted for and everything has a full outer shell. So this can simplify to a chemical formula of ALN, a 1-to-1 ratio between these two. And if we go to name it, we see on the ion side of the alchem table that Al3 plus has a name of aluminum, and N, when it gains electrons, has a name of no longer nitrogen, but nitride. And so the proper name for this compound would be aluminum nitride. All right, I would like you to pause the video, try B and C in a similar format to the one I've modeled for you, and then unpause it and see how you do. Okay, setting up part B, you may end up with the same situation that I have here. You have potassium with its 1 valence electron, giving it to sulfur, and potassium ends up having a full outer shell, but sodium doesn't. It still needs 1 more here. So the question becomes, where can that electron come from? Well, we can't just pull it out of thin air. What we can do is we could add another potassium to the mix because these things are not always happening just in a 1-to-1 ratio. These guys are so small. There's usually lots and lots of them around. So that potassium could donate that second electron to make sulfur have a full outer shell. And this second potassium also has a full outer shell because it's lost that 1 valence electron. So that means that we have K1 plus and K1 plus with an S2 minus. And this simplifies into having essentially 2 of these K1 pluses that are required in order to combine with 1 S2 minus. And so we can simply write this as K2S, 2 potassiums for 1 sulfur. And when we name it, we use the alchem periodic table. We see that K1 plus has a name of potassium, same as its element name, but S, when it gains electrons, is no longer sulfur, it's sulfide. All right, now that you know that little trick, try C. Pause the video, try it, and then check your answer with me. So let's start having magnesium lose its valence electrons to get a shell, fuller shell, and phosphorus gaining them to try and fill its. So we start by moving electrons over. This magnesium's happy, but phosphorus is still missing 1 in order to have a full shell. So we add another magnesium. That one is now full, but this magnesium still has 1 to give. So let's give it to another phosphorus. Well, now it's happy, but phosphorus still needs 2 more filled. So if we add another magnesium, we now find that all of these can have a full outer shell. It just didn't happen a 1-to-1 ratio. So that means that we have magnesium 2 plus, and it took 3 of them in order to combine with phosphorus, which has a charge of 3 minus, and it took 2 of them. So the chemical formula that results from the combination of these two is Mg3P2, 3 magnesiums to 2 phosphoruses. And the name of it becomes magnesium from the ion side of the table, and phosphorus becomes phosphide. One more scenario that I'd like to run by you is a scenario where we look at some metals that have very special properties. If you look on the ion side of the alchem table, you'll see there are a number of transition metals that have more than 1 valence, and they have this sort of split box appearance on that periodic table. Let's look at lead, for example. It's element number 82. We see that it can be a 2 plus ion or it can be a 4 plus ion. And so what happens in these scenarios? How can we name and come up with chemical formulas for these? Well, lead 2 plus and oxygen 2 minus would come together in a 1-to-1 ratio. Lead would lose 2 electrons and oxygen would take them in. So the chemical formula for this would be PbO. Down here, lead has the ability to lose 4, but oxygen can only take in 2. So it's going to take 2 oxygens to accept those 4 electrons that lead can give off. Notice the chemical formulas are the same, but if we were to name these based on what we know right now, we would discover that they're both called lead oxide. However, they both have different physical and chemical properties, and so we use the charge that's on here as a Roman numeral here to show which one is being used.